The ALMA array has recorded many fascinating variations on disk geometry, and in this video, we're going to look at the three primary disk classifications: protoplanetary, dust, and transition. So the ALMA array records in the microwave to infrared range, which is suitable for cold disks. And one of the interesting things about this array is it has 134 million processors performing up to 17 quadrillion operations per second in order to mesh together the data from all the different telescopes. So we'll be looking at three types of disks. First, a transition disk around TW Hydrae star. Those are disks with outer protoplanetary sections and inner debris sections. Second, we'll look at a protoplanetary disk around HL Tauri, another star. And that's a disk with a disk atmosphere and mid-plane dust layer throughout the entire disk. It's optically thick, which means they can't see through it, but it might have gaps where planets are forming. Finally, we'll look at a debris disk or an older disk. And we'll be looking at B883 Orionis, which actually is not an old star, but it's a large star, so it's blown away the disk quickly. And in a debris disk, the disk atmosphere has been stripped from the disk, leaving behind dust and debris. And like the others, it might have gaps where planets are forming. So the three stars we'll be looking at are TW Hydrae, which is a K6 star, HL Tauri, which is slightly larger and a K9 star, and then B883 Orionis, which is a young star that's 30% more massive than the sun, but 400 times more luminous. So here's the sun, and to be 400 times more luminous, it would be up in this range. So here's TW Hydrae transition disk. And so it's a relatively old star, it's 8 million years old, and it's relatively small, K6. It has a transition disk, which means a dusty inner disk and an outer gas disk. It also has a hole inside of the dusty inner disk of about 1 AU. And then the dust disk extends from 1 to 4 AU. And then the gas or protoplanetary part of the disk begins to expand at 4 AU. There's probably a planet in a gap at 22 AU. And there's also, they can detect different gases at different spectral frequencies. And so they've noticed that a carbon monoxide gas begins at 30 AU and extends to 200 AU. So here's the inner hole, and each pixel is about 1 AU. So this is the inner hole that's 1 AU extending out from the star. This whole picture is about 4 AU. And just one interesting fact is if this is 1 AU and the star is 175 light years from Earth, that means that this distance across here is 1/10,000,000th of the distance to the star. So you can imagine what a small angle that is. But they're able to do that with a large telescope array. At one frequency, they can detect carbon monoxide, so this begins at about 30 AU from the star and extends out to, I think, 200 AU. They also can detect methyl alcohol or methanol at 30 to 100 AU from the star. And then this is the gap where they think a planet is forming at 22 AU. Okay, here's the next star we're going to look at. This is HL Tauri, which has a protoplanetary disk. And this star is about 100,000 years old. It's a T Tauri star, which means it has jets coming off the star above and below the disk. It's between the size of the sun and TW Hydrae. It has a radius of 80 AU, and it's 0.13 solar masses. The disk is optically thick, which makes sense since it has gas, it's a protoplanetary disk. And there are gaps in the disk that indicate that planets are already forming in the gaps. So if we go back here, I'm not sure exactly where the planets are forming, but scientists can't directly observe the planets, but they can see if the star is oscillating back and forth to see if the gravitational effect of the planet is pulling on the star. So they first can see the disk's gaps, and then they can look at the star's wobble to see if any planets are affecting the star. Finally, we'll look at the V883 Orionis debris disk. And so this is a very large star. It's only about 100,000 years old, but it has already blown away all the gas from above and below the midplane dust layer. And one thing you can see here is the inner part of the disk is hot, and all the water has sublimated to the gas phase, from the ice phase to the gas phase. But out here, it's still cool, far away from the star, and so this part of the disk has ice on the dust. And so this is called the snow line. Just like there's a snow line on a mountain, where above the snow line there's snow, and below there's not. Well, it's the same thing in disks. So this doesn't have any disk atmosphere, and so it is called the dust disk. So scientists have looked at different disks and ages of stars, and they've calculated how long protoplanetary disks last. And just one reference point is after 3 million years, approximately 20% of the stars still have protoplanetary disks. For 10 million years, almost no stars have protoplanetary disks. And this is why large gas giants have to form quickly before the protoplanetary disk dissipates. We'll see you next time.